The Big Bang Theory is a scientific model that explains the origin of the universe. According to this theory, the universe began approximately 13.8 billion years ago from an extremely hot and dense point called a singularity. This singularity rapidly expanded, spreading matter and energy across space. The Big Bang Theory has profound significance as it provides a comprehensive explanation for the observed expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements. Before the Big Bang, the universe was in an unimaginable state of compression. However, within a fraction of a second, it began expanding and continues to do so today. Understanding the Big Bang helps us comprehend the fundamental processes that shaped the cosmos, from the formation of galaxies to the intricate structures we observe today. This theory is a cornerstone of modern cosmology, offering insights into the very fabric of space and time. In the earliest moments after the Big Bang, the universe was an incredibly small, hot, and dense point known as a singularity. This singularity contained all the energy, matter, and space that would eventually become our universe. At that point, time and space as we understand them did not exist. Then, in a fraction of a second, the universe began to expand rapidly in an event known as cosmic inflation. This rapid expansion caused the universe to grow exponentially, stretching space itself and cooling down at an astonishing rate. Imagine the universe growing from the size of an atom to that of a galaxy in less than a heartbeat. During this initial phase, the universe was a hot soup of fundamental particles like quarks, electrons, and neutrinos. These particles were moving at incredible speeds with immense energy, interacting with each other in a highly chaotic environment. The forces that govern the universe, such as gravity, electromagnetic force, and nuclear forces, began to emerge and separate from one another, setting the stage for the development of complex structures. As the universe continued to expand and cool, it reached a point where quarks could combine to form protons and neutrons, the building blocks of atomic nuclei. This process of expansion and cooling was essential for the formation of matter as we know it. From this point on, the universe's evolution would be driven by the forces of gravity and nuclear fusion, leading to the formation of stars, galaxies, and everything we see around us today. Thus, in these first critical moments, the foundations of the universe were laid, framing the structure and behavior of the cosmos that we now strive to understand. The birth of the universe is not just an explosive beginning, but the moment when the intricate dance of particles and forces began, setting in motion the grand story of cosmic evolution. In 1965, Arno Penzias and Robert Wilson made a groundbreaking discovery while working with a radio antenna at Bell Labs. They detected a faint, persistent noise that seemed to come from all directions. This noise wasn't from any known earthly interference or celestial object they were aware of. This mysterious signal turned out to be the cosmic microwave background radiation, often abbreviated as CMB. The CMB is a faint glow of light that fills the universe and can be detected in every direction, providing a snapshot of the infant universe about 380,000 years after the Big Bang. At this early stage, the universe was a hot, dense plasma of particles. As it expanded and cooled, it reached a temperature where protons and electrons could combine to form neutral atoms, allowing light to travel freely for the first time. This light has since stretched into microwave wavelengths due to the expansion of the universe, creating the background radiation we observe today. The importance of the CMB cannot be overstated. It serves as a crucial piece of evidence for the Big Bang Theory, supporting the notion that the universe originated from an extremely hot and dense state. Detailed measurements of the CMB, such as those from the Planck satellite, reveal tiny fluctuations in temperature, which correspond to the seeds of galaxies and large-scale structures we see in the universe today. These observations align with predictions of the Big Bang Theory, solidifying our understanding of the universe's origins and evolution. In essence, the discovery of the cosmic microwave background radiation provided a window into the earliest moments of the cosmos, offering compelling evidence that transformed our comprehension of the universe's birth and development. In the moments following the Big Bang, the universe was a hot, dense soup of elementary particles, including quarks, gluons, electrons, and neutrinos. It was a chaotic environment where high temperatures and energies led to frequent collisions between these particles. As the universe began to expand and cool, these conditions changed. allowing particles to interact and combine in more stable ways. One of the most critical processes during this period was nucleosynthesis. This process began just a few minutes after the Big Bang, when temperatures dropped enough for protons and neutrons to collide and stick together. Through a series of nuclear reactions, these conditions led to the formation of the lightest elements, primarily hydrogen, along with significant amounts of helium and trace amounts of lithium and beryllium. Nucleosynthesis was a short-lived but crucial phase, lasting for only about 20 minutes. During this time, the intense heat and pressure facilitated the fusion of protons and neutrons into atomic nuclei. Given the conditions, the ratios of these light elements generated were very predictable and have been well verified by astronomical observations, providing strong evidence for the Big Bang theory. As the universe continued to cool, electrons began to slow down and were eventually captured by these nuclei, forming neutral atoms in a process known as recombination. This critical phase occurred roughly 380,000 years after the Big Bang. It marked the first time that light could travel freely through space instead of being scattered by free electrons, leading to the decoupling of matter and radiation. The photons from this time have traveled through space for billions of years and are now observed as the cosmic microwave background radiation, a faint glow that permeates the entire universe. Once neutral atoms formed, they began to clump together under the influence of gravity, gradually leading to the formation of larger and more complex structures. Over millions of years, these clumps of matter developed into stars and galaxies, eventually giving rise to the rich and intricate cosmos we observe today. From these humble beginnings, matter evolved through complex interactions in various phases, eventually leading to the diverse array of elements we see in the universe today. This intricate dance of particles and forces set the stage for everything that followed, from the formation of stars and planets to the emergence of life itself. As the universe continued to expand from the initial Big Bang, it began a process of cooling. In the first few minutes, temperatures were so high that only elementary particles could exist. As the universe expanded, the temperature dropped rapidly, allowing these particles to combine and form simple atoms, primarily hydrogen and helium. Over hundreds of millions of years, gravity worked its magic on these clouds of gas. It pushed atoms together, causing them to coalesce into denser regions. These regions became the seeds of galaxies and stars. Gravity pulled the hydrogen and helium into large clumps, and as the gas clouds collapsed, pressure and temperature increased inside these clumps. When conditions were right, nuclear fusion ignited, creating the first stars. These early stars were massive and short-lived, ending their lives in spectacular supernova explosions. These explosions scattered heavier elements like carbon, oxygen, and iron throughout the cosmos, enriching the interstellar medium and creating the building blocks for future star and planet formation. Over billions of years, galaxies formed and grouped together, merging into larger structures. The cooling process also allowed complex molecules to form, eventually leading to the formation of planets around new generations of stars. Planets within these systems varied widely, from rocky worlds like Earth to gas giants like Jupiter. As galaxies formed and spread out, the universe continued its expansion, making it colder and less dense. This ongoing expansion and cooling have shaped everything we observe today, from the majestic spirals of galaxies to the stars that illuminate our night sky and the very atoms that make up our bodies. Today, the universe we observe is an expansive tapestry of galaxies, stars, and cosmic phenomena. Our observable universe stretches roughly 93 billion light-years in diameter, filled with hundreds of billions of galaxies. Each of these galaxies houses star systems, nebulae, and an incredible variety of cosmic structures. The distribution of these galaxies is far from random. They form a vast, intricate web known as the cosmic web, consisting of filaments, clusters, and voids. These structures emerged from initial slight density fluctuations in the early universe, amplified by gravitational forces over billions of years. Modern technology, such as the Hubble Space Telescope and other sophisticated observatories, has allowed us to explore this immense universe with unprecedented detail. From our position in the Milky Way galaxy, we can observe and study light from distant galaxies, some billions of years old, offering us glimpses into the universe's history. Understanding the current state of the universe not only satisfies our curiosity, but also provides crucial insights into fundamental physical laws and the universe's ultimate fate.